So I'll start. So hi, I'm Anoop. I also work for Western Digital Systems Software Group along with Atish and Offer. So I'll be talking about RISC-V hypervisors, and as the topic suggests, it will be all about the hypervisor spec and the various hypervisors that we have ported. So broadly, we have three topics to talk today, and first is the spec, and we'll spend more time in the spec, and also even have slides to show apple-to-apple comparison with ARM and other, particularly ARM architecture. And then we'll also look at the status of the KVM RISC-V and XYZ RISC-V project, and based on time, we'll try to cover the software part more. So starting with the RISC-V H extension, or the hypervisor extension as we call it. So RISC-V is not just one ISA, it's actually a set of ISAs where each ISA is targeting a particular functionality. And so H extension is an ISA which targets the hypervisor functionality for RISC-V. And it's been in development since like more than 2 years now. The key contributors for this spec are Andrew Waterman, John Hauser, and Paolo Bozzini. And so there have been like 5 draft releases so far. And recently there have been 3 draft releases because of our efforts. And then there will be one more draft release, that is 0.6 with a minor change left based on the feedback from the SCL L4 hypervisor folks. But this change won't impact the other hypervisors that we have ported, that is XYZ and KVM RISC-V. And as per the members meeting which was held in recent RISC-V summit in December 2019, so this will be like the last draft release, and spec will go in frozen state. So we can expect the H extension spec to go in frozen state like in next couple of quarters, and probably by year end it will be even ratified. So, Western Digital has been doing a lot of code development for the hypervisor spec or the H extension spec. So we are using QEMU as our RISC-V implementation, and we are using XYZ and KVM as the 2 different hypervisors to validate the spec. And this is the timeline shown of the various draft releases and at what point we open sourced which patches. So and over the time we have actually contributed a lot of feedback to the spec community, and because of that feedback, actually, if you see recent 7 months, there were 3 draft releases, because with every draft release we re-implemented everything and just gave feedback, and most of the feedbacks are around the feasibility of software implementation or an actual implementation, and then how performance is impacted, and so. And the lower small boxes, fonts are small, it's not readable, but yeah, these are the different patches that were upstream at different points in time. Yeah, and we are expecting a 0.6 release soon, and it will go in frozen state by that. So what changes are there in RISC-V ISA due to H extension? So there are some mode changes, privilege mode changes, but the overall idea is to make the H extension packs suitable for both type 1 as well as type 2 hypervisors. And so we have a new HS mode for hypervisor, which is nothing but an S mode with additional hypervisor capabilities. So any traditional S mode OS will continue to run in HS mode unmodified. You don't need to do any special changes to run an HS mode. And then we have 2 additional modes for the guest, that is VS mode and VU mode. VS mode is like virtualized S mode for running the Linux inside a guest or VM, and then VU mode is for the guest virtualized user space. So in HS mode now we have 3 types of CSRs. One is a traditional S mode CSR prefixed by just S, and then we have H prefix CSR which are for the hypervisor capabilities, and then we have VS prefix CSR which allow HS mode to access the state of the guest or VM or the VS mode registers. And in VS mode, whenever Linux does an access to S mode CSR, it will not go to the actual S mode CSR, it will actually map to the VS mode CSRs. So, and this is the layered different privilege modes, and the color coding is used for a different color for different privilege mode. So hypervisor is like the red one, and the VS and VU mode are green and blue ones. Yeah, so these are the list of all the CSR that are added with HS modes. It's pretty small compared to the other modern architectures. Yeah, but so the left-hand side table is the hypervisor capabilities which HS mode has, and in that we have highlighted few CSRs with the red. Those are the ones we actually were added based on our feedback and based on our efforts to implement in QEMU and XYZ and KVM. And then the right side ones are the VS CSRs, which allow HS mode to access the S mode VS mode state. And all S mode CSRs are not covered in this VS CSRs. Only the critical ones are covered. and the ones which are not covered by these VSCSRs will trap and emulate in hypervisor. And just like any modern architecture with virtualization support, we also have a two-stage MMU. The HS mode and U mode will have a single stage, which is the HS mode page table. So hypervisor also needs MMU for itself. So it will have a HS mode page table, which will translate hypervisor virtual address to host physical address, and it will be programmed by hypervisor itself. And then we have two-stage MMU when we are running a guest or VM. So the guest or VM will program the stage 1 or the VS mode page table, and that will do a guest virtual address to guest physical address translation. And then we have a stage 2 page table, which is programmed by the hypervisor for each VM, which will do the guest physical address to the host physical address translation. And this is a pictorial show of how the translations work. Very similar to what is done with Intel EPT and ARM nested page tables. And coming to MMIO traps and virtual interrupts. So in RISC-V H extension, injecting a virtual interrupt to a guest VM is very simple as just writing some bits in the HIP CSR. And then we have 3 virtual interrupts as of now, which you can inject through software in from HS mode to VS mode. One is for the virtual external interrupt, another virtual timer interrupt, and virtual interprocessor interrupt. And in general, injecting a virtual interrupt or virtual interprocessor interrupt or virtual time programming are through all SBI calls. So we have SBI calls defined for those things. And guest MMIO emulation is done through the stage 2 traps, just like other architectures. It's very pretty standard thing. And the 2 prominent devices that we are right now emulating in software is PLIC. So PLIC is right now totally software emulated in most of the hypervisors that we have ported for RISC-V. And we have whatever devices which are like the para devices, which are again software emulated right now. So coming to since this is in a very good shape now, it makes sense to compare the RISC-V H extension with a well-known modern architecture like ARM64, which is now quite mature. And ARM64 is like the most recent RISC architecture which added virtualization support, so it will be easier to compare with that. We can even do a similar comparison with other RISC architecture as well, like MIPS or PowerShell, but because of our familiarity with ARM64, we chose to compare it with ARM64. So to start the comparison, actually, like I mentioned, we have privilege mode changes in RISC-V extension, but those privilege mode changes are like adding additional capabilities to S mode. We are not adding a totally isolated separate privilege mode for running hypervisors. So in case of ARM, when they released ARM v8.0, they added a dedicated EL2 exception level with their own separate CSR to run for hypervisors. And then the guest or VM were meant to be run, or they run in EL1 and EL0. But in case of RISC-V, they run in VS and VU mode. So this is the approach that RISC-V took is actually suitable for both type 1 and type 2 hypervisors. But in case of ARM v8.0, the first release of the ARM64, it was not that much suitable to type 2. It was suitable to type 1, but then there was a lot of context switching overhead for type 2 hypervisors, because the world switch will lie in the EL2 mode and the rest of the host kernel will run in the EL1. So there was a lot of back and forth switching between whenever there was a VM exit, particularly for type 2 hypervisors like KVM. So they realized that fact, and then in ARM v8.1 they improved it, and they came up with a VHE extension, the virtualization host extension in ARM64. This is nothing but a very giant aliasing where you have a host kernel, a Linux kernel, which is meant to be run in EL1, and they want to run this in EL2, but they want to fool the kernel. So what they'll do, they'll map all the EL1 accesses to EL1 CSR accesses to EL2 MSRs. And similar aliasing is also there in case of H extension, but this is more at the VS mode level. So where all the S mode CSR access from the VS mode will map to the VS CSRs. So pretty much this is already taken care in case of RISC-V. So going forward to virtual interrupts. So like I mentioned, virtual interrupts are just programming the HIPCR is sufficient to inject virtual interrupts. We don't have a defined interrupt controller with virtualization support as of now. So that's why interrupt control is totally software emulated right now in RISC-V world. And for save restore overhead of virtual interrupts, we just need to save restore two CSRs, HIP and HIE. Coming to ARM world, actually most of the cases across hypervisors, the virtual interrupt is injected by programming the LR register of Geek V2 V3, and this is good because there is no trapping as such. The VM will directly access the CPU interface registers, and the other part of the geek will be trap and emulated, but there is a context switch overhead. So whenever there is a context switch, all the complete hypervisor control register, including the LR register, will be saved and restored. And moving towards the virtual interprocessor interrupts, they are through SBI calls in case of RISC-V, so which will again trap. And then in case of ARM64, these are also trap and emulated, because whenever guest or VM accesses the ICC, SG1, EL, these two registers, they will trap and emulate in hyper. They are not virtualized by the hardware. And for virtual timer events, in case of RISC-V, we have an SBI call. So since it's an SBI call, it will again trap and be emulated by the hypervisor. And in case of ARM, they have virtualization support in the generic timers itself. But this means that hypervisor will have to save, restore the virtual timer state on every context switch. And lastly, nested virtualization. So functionally, nested virtualization is already supported and considered in the RISC-V edge extension spec. So everything which is required for hypervisor to implement the nested virtualization is there. The only thing which is not there right now in RISC-V edge extension is a special acceleration to reduce the number of traps while you are doing nested virtualization. But in case of ARM, the most recent ARM v8.4 has support for nested virtualization, and also the enhancement to accelerate the nested virtualization. Yeah, the only downside with ARM was like nested virtualization was not defined from start itself. They realized late and they added with ARM v8.3. But for RISC-V, it's already defined and well spec'd out actually. And so what's the future work on the spec front actually? So like I mentioned, most of the things functionally required from the spec are there. Most of the things we can expect now will be on the performance front, like optional acceleration for nested virtualization or optional acceleration for stage to dirty page tracking, like other like Intel and other the architectures have. And some changes will be there in the spec, SBI spec as well. We need a per-hour time still accounting API. Then we also need an SBI extension for guest time scaling for migration for across hosts with different timer frequencies. And there are two new specs also being drafted, and they'll come up like over the years. One is a new interrupt controller with virtualization support and MSI support, and then there'll be a new spec for IMMU as well. And if you have any suggestion, please feel the community is open for ideas. Yeah, please write. So now we'll talk more about the software status of the different hypervisors that we ported. And I'm sure I'm running out of time, but I'll try to catch more. So first talking about the KVM RISC-V, it's the type 2 hypervisor that we first ported for the RISC-V world. It's pretty, so the key aspects of the KVM RISC-V port that we contributed was like we didn't actually change the KVM ABI. There was no new ioctals added. And the world switch is really minimal possible because the CSRs are very less compared to other architectures. And we have a vCPU load put interface for lazy save restore of most of the full world switch. And then we have KVM 1 reg interface for user space to access the vCPU state. And then for guest or VM, the hypervisor will emulate the SBI 0.1 interface. And like I mentioned, Plick emulation is done in user space, totally in software. We also have huge page support, and all the undefined SBI calls will be forwarded to a user space. Yeah, and this is the software layers involved. And so where are the patches? So like we contributed the patches, first version was like in July 2019, and all the patches were reviewed pretty fast. By V6, everything was agged and reviewed. And by V10, so recently we contributed V10. So this was rebasing everything to the recent draft release, that was 0.5 release. And recently we also started sending out the KVM tool patches, and so far we are waiting for more comments. It's at RFC V2. We are holding the QEMU KVM upstreaming right now. We are working in background, but we are not upstreaming anything because we want the KVM RISC-V to be merged in kernel first. And then here are some of the important links. So this is the developer repo or the maintainers repo. And then we also have created a mailing list because KVM RISC-V is not just about the kernel support. There's also user space pieces like libvirt, QEMU, KVM tool, and other pieces. So for that, we have a common list where you can CC all the patches. And then we also have a wiki setup on GitHub as well. We right now have one page, important page, where you can, using the steps over there, you can just replicate whatever we have done so far. And this is like a brief to-do list. It will keep growing, yeah, but we need to get 30-bit working, add SBI 0.2 support, trace point supports, KVM unit test support. virtualized vector extension, that's another thing which will be frozen soon. So, and then QEMU KVM support, then nested virtualization support, migration support, and the last two also is like for completeness, like 32-bit guest on 64-bit guest, or allow big Indian guest on little Indian, and those two things are already spec'd out. They are already there in the spec. So moving to the other hypervisor that we ported, I'm sure we have some time. So it's the type 1 hypervisor, bare metal type 1 hypervisor open source. It's much simpler compared to the KVM approach. It's just one monolithic layer running entirely in HS mode. XYZ is called, it stands for Extensible Versatile Hypervisor. It's a GPLv2 bare metal hypervisor, and like it's not new project. It's been there around like more than 9 years now. And this is the website and the mailing list, and it supports all the family of ARM and Intel 64-bit and RISC-V now. So there was a recent release like in the start of Jan, which has RISC-V H extension support, a working RISC-V H extension support with compliant to 0.5 draft. It's able to boot multiple guests with SMP, and also able to boot Open Embedded or Fedora as guest OS. And here are some of the documentation. There is a documentation text file in the source itself. You can follow that. And there is a work in progress QEMU we have hosted, which has the emulation support, which is over here. And please join the mailing list if you are interested in this project. And same, the to-do lists are pretty much same as KVM RISC-V. We need to get a 32-bit working, add SBI 0.2 support, and then there is one new item, like we want to use the unprivileged load store. It's a special thing there in RISC-V spec. We want to use it with XYZ and to speed up the guest RAM access. And loadable module support is not there. It's there in XYZ ARM62, but it's not there in XYZ RISC-V, so we want to add that. Other things are pretty much same as KVM RISC-V. So questions if we have time. Okay, cool. No questions. Cool. Either I did really bad or it was okay.
I have a question.
Yeah.
What's the process for the stuff you're doing going into chips?
For process for?
For the hypervisor.
So your question is, what is the process for the stuff we do to go into the Western Digital Silicon? So
Broadly across the RISC-V community.
okay, so different organizations will have their own process to tape out or manufacture the chip. But what I have tried to talk over here is the process that RISC-V Foundation follows, how it freezes, how it defines a spec and freezes it. So the first slide, yeah. So if you look at this, so this tries to show a high-level skeletal process. So any new spec in RISC-V starts with a draft, goes through various revisions, and then eventually it enters a frozen state, and then eventually it is ratified. So after frozen state, there is no functional changes at all, and then it's only the wordings and or errata workarounds or something, or erratas to be redefined, and then it enters a ratified step. So the whole process of the defining a RISC-V extension, extension in RISC-V is designed around that. You take a lot of time to define the extension, so that it is long-lived enough